speaker is Professor Stefan Töpfl. Stefan is a food technologist and received his PhD in food process engineering at Berlin University of Technology in 2006. As process specialist at the German Institute of Food Technologies, DIL, he has been active in process design and realization of processing equipment with a focus on pulsed electric fields, static and dynamic pressure applications, supercritical fluids, as well as plant protein extrusion. Since 2009, he is a professor at the University of Applied Sciences, Osnabrück, Germany. Since 2017, he is managing director of ELEA GmbH, a spin-off entity for marketing innovative processing technologies for the food industry. His research interest is focused on efficient and sustainably food production techniques, plant-based protein processing, and process automation. Over to this presentation.
Hello, everybody. My name is Stefan Töpfl. I'm very happy to contribute here to the symposium on potato science and potato technology with a talk about PEF use in that industry sector. I'm managing director of ELEA, which is a company dedicated to pulsed electric fields or PEF systems into the food industry and the potato industry. And the process is based on electroporation, or as we like to call it, eleoporation, triggering cell membranes and opening up cell membranes by high voltage pulses. These high voltage pulses are causing a pore formation on an effect based on electroporation. So we charge the membrane, we shoot through it, we open a pore, and through that pore then the liquid inside the cell can leave, and we have an open path for mass transport into or out of the cell. The factors defining if that is successful or not are the electric field strength, so the intensity of the pulse and the amount of energy we apply, and by the amount of energy we can also change and control the pore size, which can be visualized very well on potatoes, as you see on the picture here. On the left, we have a control, in the center a low, and on the right side, a high PEF treatment. And you will see the control has almost no moisture. The low PEF treatment has a moisture film, and the high PEF treatment has a very strong leakage or very wet surface. This is defining how much water is coming out. The water leakage is causing a softening of the tissue. The turbo pressure is reduced, but that's also already indicating that those products will dry faster, or that you can manage to wash the sugar out or to get salt into such a tissue. As mentioned, turbo pressure is reduced by pulsed electric fields application, and associated to that there is a reduced cutting force, typically around 50% less force to press a potato through a grid or cut it with a knife, which has the benefit of reducing the amount of feathering. So potato strips show less breakage, show less cracks, and those cracks are typically causing the product to be shorter, but are also the exit point for starch and the entry point for oil. So after a PEF treatment before cutting, we will see a reduced starch loss, a higher yield, and we will see a reduced oil uptake, so less fat in the final product. That reduced starch loss is typically in the range of 1%, or reduced from 14 to 5.6 kilograms per ton of product processed. And on a standard sized line of 8 ton per hour final or 16 ton per hour at the stage of PEF, this is a 43,000 euro saving potential per year. PEF is therefore often applied in French fries processing before cutting, can be before or after peeling. That doesn't really matter, but has to be before cutting, because here the major benefits are seen. And PEF is replacing a standard preheater, 60 degrees, 30 minutes, that was used before PEF was applied in that industry sector, where PEF has benefits in energy and water savings and less time requirement than the cooking. At the moment, we have installed 175 machines in potato processing industry worldwide, Europe, North America, South America, but also New Zealand, Australia are the areas where those systems are placed in different sizes, ranging from 1 ton per hour up to 60, 70, and in the latest installations, 100 tons per hour throughout. PEF has a Substantial impact on sustainability of a line, and the numbers are shown here. We save electric energy, 10 million kilowatt hours per year. We save water usage, 24,000 cubic meters per year. And as already mentioned, there is less oil uptake, 360 tons per year, and a higher yield, approximately 1,000 tons per year. All of that on a line where 26 tons per hour of raw material is processed. So the benefits are dependent on the throughput here. All in all, those benefits pay for a machine typically between 12 and 18 months would be the standard return of investment times for such an application. PEF is rolled out now from French fries into potato and vegetable chips processing. The benefits are similar. We can slice better. We have less starch losses, less breakage, less fines. We see less doubles. Doubles are slices which are sticking together in the fryer, and the sticking is caused by starch. So as you may imagine, less starch on the surface means less sticking. So for potato chips, vegetable chips, approximately 1.5% yield increase is observed. And we have opened up the potential to cut raw materials which are difficult to slice, like taro, sweet potato, kumara, cassava, manioc, which after PEF can be sliced into flat slices, V-cut, crinkle cut, or many other shapes. The leakage or the faster exit of water is causing a reduction in frying time, as seen here. The blue curve, the heat is coming up faster. The frying time can be reduced by 10% because the water is removed faster in such a fryer. Overall, frying time and frying temperature can be reduced, and that is increasing the line capacity of a frying line. 10% of time, 5% more batch size because of less doubles gives an overall 15% capacity increase. And again, PEF is applied before slicing here because that's the way to utilize all those benefits in the subsequent processing steps. I've mentioned oil uptake reduction already for French fries. The same effect is seen for potato chips. A smoother surface does not allow oil to get in that easy, and the faster moisture removal is countercurrent to the oil uptake. So we see an approximately 5% reduction of oil uptake, which improves the product sensory, texture, but also health aspects of the product. For vegetable chips, we see much lighter color. Again, this is a result of reduced frying time and frying temperature. Top row here untreated, bottom row PEF treated, all of them get lighter or more natural in their color, and associated to that reduction in the frying time and frying temperature, vegetable chips will also show reduced acrylamide numbers because of less heat load, less heat damage during the frying process. A higher starch yield will also cause a better crunch. More starch in the product means more solids, more dry matter. Sometimes this is desired, a more kettle style product. Sometimes this is undesired. If the product is getting too hard, which sometimes happens, we are modifying the frying conditions to even lower frying time and temperature, which also is good in terms of yield, because a little bit higher moisture can be left in the product after PEF without any compromise on the crunch, and therefore yield as well as product quality can be optimized with the right optimization of a line. For potato and vegetable chips, we have designed smaller scale systems. This is a 1 to 6 ton per hour system, compact design, which fits well for white potato, sweet potato, but also other vegetables. And it's the standard design for chips or snacks lines. What else is coming up? We're currently looking a lot into texture management by past electric fields. The effect is based on pectin methyl esterase, or PME, an enzyme which is causing a dimethyl esterification, and in combination with calcium that can cause a hardening or texture management. PME has a temperature optimum of 50 to 70 degrees. So this works when applying PEF, releasing the enzyme, and then applying a holding time or cooking or heating time at 60 degrees centigrade, more or less. The pectin will be deesterified, and then an egg box model can happen. So calcium will cause a cross-linking and the texture is getting harder. This can be seen on these cooking curves here. Blue is the standard treatment, orange is the one with PEF. And as mentioned before, PEF will make the product softer, as we see here at minute 0. But when we hold the time or with increasing cooking time, this effect is reverted. The orange line then is showing a higher cutting force than the blue line, which means we have made our potato more resistant against the cooking. It's showing less softening over cooking, which is interesting for retorted or canned products to manage the texture and make it more better surviving a cooking process. Some more research has been done in that area by K. Löwen, where additional calcium addition helps to even have this effect more pronounced, PEF plus 60 degrees centigrade, and calcium helps to reduce the hardness loss in cooking for even longer times and is interesting for retorting processes. And similar effects or similar studies have also then been done evaluating the impact of that combination on stored potatoes. And even after 20 weeks storage or 32 weeks of storage, that effect is still there. So a combined PEF and heat application can be applied to reduce the susceptibility against heat or to better maintain the texture of the product after a heating, canning, retorting process. We've started to install first industrial lines in the systems for potatoes and for sweet potatoes, confirming those results that you can make potatoes and other vegetables more resistant against the heat treatment with that combined effect, pulsed electric fields, pectin methyl esterase, and then a holding time at heating. In most products, you have to say calcium addition is not possible because there's enough calcium in the product. So summarizing here, PEF has a number of benefits for vegetable products. It's opening up the cells. It can accelerate drying. For fries and chips production, we see cutting and yield benefits, less starch loss, reduced oil uptake. And when we talk about cooked, canned, retorted products, we see a very good potential to achieve texture management. And whilst we are making a softer texture, the texture is better maintained over subsequent processing steps. And in particular, we can harden the product and make it more resistant against cooking. And those are applications where we expect further research, but also further industrial use of the technology in the future. We're operating an own test center in Germany. We have rental systems, batch or continuous, 1 to 6 tons per hour or 10 kilograms. There are also systems available in New Zealand and Australia. So whenever you're interested in running trials or finding out what PEF does to your product, we're there to help and to support. And you will find the contact details on that last slide here. I would like to thank the authors for inviting me to contribute here, and I'm looking forward to discussing with you all as soon as possible. And yeah, thanks for listening and thanks for joining in.
Thanks, Professor Stefan, for your presentation and for providing a good overview of the use of PEF in potato processing. Good to know how industry is looking at new innovations like PEF. No doubt it's one of the fastest growing technologies in the area of food science and technology. Thank you very much.